Hello, my name is Fred Jordan. I am the CEO of the company Alvision, also the co-founder. And I'm going to talk to you about the next generation AI, or what could be a next generation of artificial intelligence. So just a few words about our company Alvision. So we were founded in 2001, so it's about 20 years of innovation. We are based in Switzerland. We have offices also in the US and Shanghai. So what we are doing is software, hardware, and a lot of machine learning. So this is what I'm going to talk about today. We have also a sister company which is called Final Spark, when we do fundamental research in AI. We are quite an innovative company with over 90 patents over this last 20 years of innovation. So let's talk about neurons. Most of the hype today about artificial intelligence actually boils down to artificial neural networks. But if you see on the slide here, this is what a biological neuron should look like. So basically you have the core of the neuron, you have dendrites, you have the axon going back. So this is a very complex and messy thing. So in practice, the implementation, software implementation, the mathematical model that is used is shown on the right hand side. It's much simpler. Of course, we have some weights simulating the dendritic connections, integration of the function, output of the neurons going through the axon, and that's it. Very simple and coarse model. But this is what is used everywhere in artificial neural networks. Most of the community is using this kind of model. And right now, the result is that it performs amazingly well. Although it's very crude, it works well, particularly for image recognition, analysis, video processing, enhancing resolution. It outperforms all of the algorithmic and signal processing approach by far. It even works to some extent to predict chemical reactions, analyze and predict protein structures, folding. So that's an interesting thing to do. Where it definitely fails, it's if you want to use it to and expect that it's going to understand or to propose new concept, the artificial neural network is not going to make it, not at all. Actually, the core reason why it's not going to make it is that AI is actually stupid, just stupid. Let me give you an example of this. So what is shown here on the screen is actually a webbot that you can find online. And she is the winner of the Turing test 2019. So that means the Turing test is, if you pass the Turing test with a machine, that means that you've made a machine as smart as the human being. That means if you discuss with such a bot, you are not able to make the difference with a human being. So it's called a chatbot. Let's see how it performed. I just had this discussion with her and I said, what do you think I should present at Intelligent Health 2020? And then she answered, are you asking me for advice? And I said, absolutely. And she said, specifically, what kind of advice do you want? And I said, what I just asked above. And then she answers, take it easy, you said absolutely. So at this point, it's clear that she did not understand anything. It's a total failure for passing the Turing test, and she is the winner. This is the best you can find. And this is definitely stupid. So this doesn't work. Actually, we need something totally different. We need a better AI. Think about this. If you look at your brain, we're talking about 100 billion of neurons. And each of them is running a realistic neural model, the real one. We see the neuron model is very complex, the real one, compared to the mathematical one that we're using in implementation. So what we should do actually is copy what already works. Copy the brain. How can you do this? Think about this, 100 billion of neurons. The power consumption related to this in your brain is 20 watts. Okay? If you want to do this by simulation nowadays, even with the very crude model that we've seen before, we're talking minimum, absolute minimum of 20 megawatts. Okay? And for this, you don't have the training wired. Okay? We just have the relaxation and you get the result. So this is not the way to go. We're not going to make it with artificial neural networks. It's not the way to go. One thing very obvious would be to use actual living neurons. And this is what we're doing. So what you're seeing here is a neurosphere. It's a conglomerate of something like 1 million of neurons, human neurons, produced by induced pluripotent stem cells that we expanded, differentiated into neurons, and this sphere is about 300 micrometer of diameter. So we built it in our lab, and this works this way. We take this neurosphere that you see here, and we put it on electrodes. And we put the whole thing in an incubator where you have 37 degrees, 80% humidity, 5% CO2. This is to ensure the regularity of the acidity of the medium. And then we have a circulation of this medium, this DMEM medium, going around these neurospheres and providing nutrients, in particular to the neurosphere. That's not enough. Actually, we have analog to digital converters to take the electrical signal from the electrodes, plug it into a computer, and the computer is able to send back actual stimulations to the neurospheres using these electrodes. So this is the full loop. On the top of it, we add deep reinforcement learning, or actually any kind of AI system that we can find to optimize the spatiotemporal electrical signal that we send to the electrodes in order to get specific results from our neurosphere. So what we want to accomplish is to train it to do something special, something useful. So like a living computer, if you want. So it looks like this. This is called a multi-electrode array. You see in the middle the 4 locations where are normally located the neurospheres. On the left you have the connector that connects to the electrodes. On the right hand side you see the tubes that provide the medium, which is circulating 24/7. So not only we are measuring these spikes, we are actually putting them directly on our website, bioserver.net. You can see them in live 24/7. They are always there. Now, so this picture we show with 2 MEAs, but nowadays we have 4 MEAs. And you see for each of the electrodes the signals which we are recording. And on the top you have actually a live picture of the MEA, which is being captured inside the incubator, which is in our lab in Vevey. So this small video shows actually a real capture for 4 neurospheres, and you see the signal for each of the electrodes. The range is from minus 100 microvolts to plus 100 microvolts. And you see this is the spontaneous spiking activity recorded from the different neurons. So what do we do with this? The goal actually is to modify the neurons in order to change their behavior. One of the ways to change their behavior is actually to use electrical stimulation. For this we are using this kind of diagram. So this is the result of one month lifetime record that we had these neurons, and at the end we perform the stimulation, and what you see vertically is the activity which is counted in spikes per minute. Okay, and this is after we performed a specific stimulation pattern. Horizontally you have the spontaneous activity before we had our stimulation applied. So each dot represents 1 electrode. So if you had actually all the dots on the y equal to x equation, you would have the effect that with your stimulation had actually no impact on the rate of spontaneous activity. What we see here actually is that after stimulation, most of the dots have gone on the top of the y equal to x equation, which means that we have actually been able to change the spontaneous spiking activity frequency of these electrodes, therefore of the neurons which are connected to the electrodes. So this is what's called long-term potentiation. We try to change the long-term behavior in order to program our computer. But imagine, this is like we are starting with the transistor, like in the 50s actually. We are trying to build a computer from scratch here. Well, still many things to solve. The first challenge is to get homeostasis. That means long-term maintaining in life of these neurospheres. So far the record was about 6 weeks. We need to perform it for more than 1 or 2 years of total 24/7 recording and healthy, active spiking activity to have something really that we can train. On the training side, of course, we are using algorithmic approach, but we are using a lot of AI, artificial neural networks approach, in order to find the optimal spatial temporal pattern, in order to learn how to teach each of the neurospheres, which by the way are all different. We have a number of technical issues. Perfusion, real-time closed loop, because we want to be very reactive when we send spikes in return of the spontaneous activity. Problems of contamination like every cell culture. Anyway, so all these problems we are going to solve them. We solve them more and more, and I hope that in the following month we will be able to actually get some basic functions of these small neurospheres, which I think is an incredible alternative approach to the traditional silicon-based artificial intelligence which is done nowadays.